Let's talk about doing arithmetic with powers of 10. You may be wondering, well, why? Because I can always punch those things into my calculator and get an answer out that way. Well, there are some advantages to being able to do arithmetic with powers of 10 in your head. The biggest advantage is that you can do a back-of-the-envelope kind of calculation without picking up your calculator. You can see what the size of the final answer ought to be. And if you punch it in and it doesn't come out to be that, then you know something is wrong. You made a data entry mistake or you typed something in wrong. So it's good for detecting errors. It's good at making estimates in advance about what the size of something is going to be. When you learn how to do this, you will gradually develop a gut feel for whether an answer looks right, the same kind of way that you developed a gut feel about whether a word was spelled correctly. So this is something that's worth practicing. And it's pretty simple. There are a couple of rules. When you're multiplying powers of 10, here's the rule. 10 to the x times 10 to the y is 10 to the x plus y. Alright, so suppose you have 10 to the 5th times 10 cubed. What's that going to be equal to? 10 to the 3 plus 5, right? 5 plus 3. 10 to the 8th. What if you have 10 to the 7th times 10 to the minus 3? We're going to add the exponents up. That's going to be 10 to the 7 plus a minus 3. I could just write that. What about this? That's going to be 10 to the 4 minus 4, which will be 10 to the 0. We hadn't mentioned this before, but if you have a power of 10 and the exponent is a 0, that's the same thing as 1. I'm going to put a box around that, which is a signal to you that that is something important to remember. All right, so remember that 10 to the 0 is just a 1. What would 10 to the 1 be? That's just 10. Maybe that's worth remembering too. Okay, so now you should be able to multiply two numbers that are in scientific notation in your head. Let's practice that. Suppose I have 3 times 10 to the 7th times 2 times 10 to the 9th. All right, well, when you're doing this multiplication, you can regroup it any way you like. And think of it as being regrouped like this. The parts that aren't powers of 10 times the parts that are powers of 10. And then it's kind of easy to do in your head once you regroup it. Now again, when I regrouped, I just put the numbers that weren't powers of 10 over here, and the numbers that were powers of 10 over here, and then I could do one piece at a time. This looks like it's going to be 6, right? And then what's this going to be? 10 to the, now you're multiplying those, so you're just to add the exponents up. 10 to the 7 plus 9, which is 10 to the 16, right? So I did that all in my head. I didn't have to pick up my calculator. Practice that as much as you can. Try to get comfortable with that. Now, what if I've got dividing? Let's put a box around that since we're doing the box thing. By the box, then I mean that's my clue that that is something to know. That is something to memorize. That is one of the rules that you should know. What if I have 10 to the x divided by 10 to the y? That's going to be equal to 10 to the x minus y. Now you can remember that rule, or you can remember one that we looked at briefly when we started to talk about negative exponents. If you have 10 to the minus x, that means the same thing as 1 over 10 to the x. You could remember just that one and this one and put them together to get this one, because this one and this one together make that one. All right, so let's practice this dividing rule here. Suppose I have, let's see, 4 times 10 to the 7th divided by 1 times 10 to the 8th. Okay, well, I can regroup this just like we did before. There's a 4 divided by 1 times 10 to the 7 divided by 10 to the 8. See how I regrouped it? If this times this and this times this on the bottom, you could make it a product of two fractions like that to simplify it a little bit. Well, 4 divided by 1 is just 4. And 10 to the 7 divided by 10 to the 8 is going to be 10 to the 7 minus 8. 7 minus 8 is going to be 10 to the minus 1. So you could write it like this. Or 10 to the minus 1 is going to be bump the decimal point over one place that way. You could write it down like that. Either of those is right. Okay? So that's how you do dividing. Now, you can adjust the size on the exponent here, and sometimes you want to do that. We're going to see you're going to want to do that when you're adding and subtracting numbers that are in scientific notation. So suppose I have a number that looks like this. And I want to make it something times 10 to the 7th. So I want to change the size of the exponent. Now what did I do here? If I go from here to here, I made this number bigger. I multiplied by 10. So to keep the number the same size, I'm going to have to do something that keeps the number the same size. Here I'm going to have to divide by 10. So whatever you do to the power of 10, you do the inverse of that to the other number. So this would be 3 divided by 10 here. So I'd write it like that. Now this is no longer proper scientific notation, right? Proper scientific notation has got a number between 1 and 10 here. And that's not between 1 and 10. But it's still okay. I mean, you could type that into your calculator and use it in calculations in this form, and it would still be an equivalent form of this. It's just not what we would call proper scientific notation. So if you make this part of the number bigger, you have to make this part of the number smaller. If you make this part of the number bigger by a factor of 10, you have to make this one smaller by a factor of 10 to keep the number the same size. Let's do another one like that. Suppose I have something like and I want to write it as something times 10 to the minus 7. So I want to find out what I need to put there. All right, now let's think about what we did to the power of 10. It went from -4 to -7. And that's like it went down. The power went down by a factor of 3. So it's like I divided by 10 to the 3, right? Because if I had this 10 to the -4 over 10 to the 3, that would be 10 to the -7. So what do I have to do to the other part of the number? I have to multiply by 10 to the 3. So it's going to have to look like this. 7 times 10 to the 3, which is 7,000. 7,000 times 10 to the -7, right? So I can adjust the size of a number that way. Whatever you do to the power of 10, you do the inverse of that to the other number that's next to it. Now, why would I even want to do that? Because that's going to be useful in what we're going to do right now when we're adding up or subtracting numbers that are in scientific notation. Suppose that I want to add suppose that I wanted to add two numbers like and I want to keep the I want to keep the significant figures correct. Both of these have two significant figures. Now, I can't just say, well, this is a 5.4 over here, right? Because the powers of 10 are different. Before I can add them, I've got to put them onto the same footing, the same size. I have got to change the powers of 10 so that they're both the same. How about I change this one so it's a 10 to the 5? So I'm going to keep this one 10 to the 5. And I'm going to change this one to something times 10 to the 5. Okay, now when I go from here to here, I made this bigger by a factor of 10, right? So I have to make this smaller by a factor of 10. Let me write it the right way. And I want to add that in. Now you can see, because you have the same power of 10, you can add these two numbers to get the answer. Now, I do not know what this digit here is. I only know this one out to the 10th place, so I'm only going to know my answer out to the 10th place. So the exact mathematical answer would be 2.61 over here, but I only know it out to the 10th place, so I probably wouldn't report that one there. So there's the sum. It'll have two figures. Now, if you add a very small number into a very large number, in other words, if the powers of 10 are much different here, you can see something surprising happening with significant figures. Let's try one like that. And it's something that can save you some work. So suppose I have 2.3 times 10 to the 5 again. And I want to add to that, let me see, 1.0 times 10 to the minus 2. So I want to add those two together. Well, now let's get them both on the same power of 10 basis. Let's keep this one 2.3 times 10 to the 5. And I want this one to be something times 10 to the 5. Now I've made the power 10 much bigger, so I'm going to have to make this one much smaller. So maybe I'm going to want to move this over a little bit. How much bigger did I make this? It went from 10 to the minus 2 to 10 to the 5. So it's like I multiplied by what? 10 to the what times 10 to the minus 2 gives you 10 to the 5. 10 to the 7, right? Because then you'd have 10 to the minus 2 times 10 to the 7 would be 10 to the 5. And that means that here, for the number that I'm going to put in here, I have to divide by 10 to the 7. Okay? So that's going to be this is 10 to the minus 1, 2, 3, 4, 5, 6, 7. That's what the number that would go there would be. 1 divided by 10 to the 7 is 10 to the minus 7. Let's double check that. 1, 2, 3, 4, 5, 6, 7. Yep. Okay, so now when you add this number, which is uncertain in the tenths place, to this number, which is uncertain way the heck out there, what's going to happen to this number? It's going to disappear completely because of significant figures, right? You only know out to the 10th. So your answer is essentially going to be just that. This number is so small compared to that one that you don't even have to worry about it. That can save you a lot of work sometimes in a complicated calculation. You'll see that things that contribute to your final answer are so small compared to other things that you can safely, because of significant figures, just ignore them.